Yesterday we had a closer look on the behavior of Eurofair steels, also austenitic steels, and today I will show you some typical applications in nuclear fusion. We focus on the blanket fabrication, and there are some very specific points which make special use of the typical behavior of Eurofair. And well, first I will show you some ideas and concepts of how to fabricate blankets, and especially blanket first wall, and then we go into some details of general joining of steels. The first wall, as you know, consists of a few hundred blanket modules. This is a drawing for a ITER test blanket module, but in principle it doesn't matter. The shape is approximately the same whether we use it or whether we will or would use it in a future demo reactor or power reactor, or as you can see here in the ITER test blanket module. There is one problem. This is a cut of the first wall, and you see there are many internal cooling channels. This is a helium cooled concept, so these cooling channels are to cool the first wall. This here is the plasma side, and you see from the dimensions they are rather tiny. There is only 3.5 millimeter wall thickness towards the plasma side. Then we have this many cooling channels with also tiny cross sections, about 14 times 14 millimeter square. And the distance of this channel is also rather tiny, it's only 5 millimeters. And if you would unbend this U-bended first wall of this blanket box, the length is approximately 3 meters. And now the problem is, you always start with a semi-finished product, and this is usually a plate. Imagine you have a plate, 3 meter long, 70 centimeter in width, and well, you can choose the thickness. So the final first wall has a thickness of 30 millimeters, so you would typically buy a plate of, let's say, 50 millimeter, and then the question is, how would you be able to, or how would you solve the problem with these cooling channels? Think a few seconds about it, but I doubt very much that you came up with a quick solution. But this is the general problem. If you want to fabricate on an industrial scale components, then there are some side issues, for example, compatibility with the industrial environment. And only a few points are that it's always useful if you could use standard fabrication processes. Robustness against the environment is also a consideration. You have to take into account corrosion due to long-term storage or whatever, rough handling in general, or if you apply some of these processes, they have to be tolerant against scattering of process parameters. Above all, it's always cost efficiency and efficiency to use resources is an issue. And finally, reproducibility. You have to perform easy quality assurance. And well, finally, dimensional accuracy has to be ensured also. Again, how would you produce such a U-bended first wall with this many cooling channels inside, and as a side issue, all the standard fabrication on industrial scale behind. Let's have a look on quite general fabrication tools. We could think about casting. You could use Eurofair, melt, and fill in casting form. You could, as I said, try to start with a solid plate and somehow drill or fabricate 3 meter long holes in it for the cooling channels. You could also think about powder metallurgy. Then you would somehow create or arrange pipes or something like that for the cooling channels, fill everything up with powder and later on compact the powder in order to result in a solid plate again with internal cooling channels. But that's not so easy. For casting, for instance, you could in principle fabricate a complete U-bended first wall. The drawbacks are here that in general you have to live with a higher impurity content due to the casting process, and it's also tricky to do this with a Eurofair steel, since 9% chromium steels are not so good for casting. So you have to take into account that you will end up with lots of voids or bubbles which are not excluded from the melt. So in general, might be possible, I don't know whether it's really the best process, but in any case you have to take into account that the mechanical properties or material properties would be not as good as before. Machining, the only possible way I can think of, or we could think of, is that you use electrochemical machining or electro-discharge machining. But there are limitations. How could you fabricate 3 meter long, precise and very narrow distance holes in a solid plate? You would have to start with producing a starting hole for example, for wire spark corrosion. And as far as I know, such machines are limited in the 1 meter range also, so 3 meters, and also drilling 3 meter deep holes through a tiny or thin plate. That's really a demanding thing. Powder metallurgy is a standard fabrication route in many cases, and it would also be possible with Eurofair. You could produce powder from Eurofair, that's not a problem, also not too expensive. In general, then the powder is compacted, then encapsulated in standard steel or whatever, put into a hot isostatic press, and then it's finally compacted near to 100%. This is possible. So 2 ways could in principle be thinkable by powder metallurgy. One is that we fabricate these long cooling channels in form of pipes, bend them, U-shape, arrange them or stack them, and fill them or surround them with powder, and then put everything in a capsule, press it together, and that's it. But, well, the problem is the same with tungsten. Powder compaction ends in a reduction of the volume, and, well, I doubt it very much that over a length of almost 3 meters, all these tiny distances between the cooling channels would be kept precisely with a distance of 5 millimeters and only 3 millimeters or so to the outer side. Do you have any further idea? I have only one left. It's the green one, that's solid state bonding or solid state welding. This comes in various types. One is explosive welding, which we immediately can forget. Makes no sense to produce first walls by big explosions. Another one is friction and stir welding. This is also not useful here. But diffusion bonding, diffusion welding, this is the choice of fabrication route, I think, which might be feasible. At least it seemed that this is promising, and it provides many different possible production routes. I will give you an overview. Diffusion welding, in that case, could be done as you have seen in the first picture. You produce the first wall in 2 halves, 2 blades. Then you can fabricate half of the grooves or cooling channels in each plate, and you have more or less to glue both halves of the first wall together, and then you end up with a complete tight cooling channel. That's the theory. So one step would be diffusion welding of such two half parts for the first wall, and start with a low pressure step to close the cooling channels. Then the weld are pressured by either hot isostatic pressing, or you could also just press the plates together by a big press in a furnace. That's uniaxial pressing. For the HIP process, you could do it with encapsulation. Usually, as I said, you wrap some metal sheets around it, weld it tight, evacuate the package, and then it can be hipped and it experiences pressure from all sides. Or you can do it without encapsulation, and then you have to use the plates, as I will show you later, as its own encapsulation. Then if you use encapsulation, you could do this with pressure plates internally to distribute perfect pressure in one direction, or I can do it without it. So you see there are already many ways to do this. And after the first step, when the cooling, or well, you consider that then the cooling channels are tight, you could open the package and apply a second welding step with a high pressure. This prevents the channels then from distortion or bending, and would finally close the steps between the channels. I know it's a bit confusing at that stage, but we will go step by step through this applications. Much research has been done, and it's a contribution of many associations and colleagues who have done these studies, and so what I show you is a concise summary of it. This is how diffusion welding is done, or how you could do it. Here are the upper and lower parts of the first wall. Internally, we have here this direction with 3 meter long cooling channels. And to avoid bending over the length, you could, or well, it's up to you, you could use molybdenum plates to ensure that you have a perfect uniform pressure over the whole length. Then the whole thing is packed into a container. It's degassed. You don't need a very high vacuum, but 10 to the minus 3 or so is enough. And then the whole thing comes into a hot isostatic press, and yeah, let's go for the test. That's one way. Here we have pressure. The second way is that you use a bit bigger plates, and you don't mill the channels through the whole plates. The ends are closed, and then you could also put both plates together, and you could perform a weld around those two plates and do this in an electron beam facility, which works already in vacuum. Then you have an automatic degassing of the whole thing, and it's completely tight welded in vacuum. So you could put this piece directly in a hip, and well, thereafter you cut the end through, and then again you have your channel. Okay, that's now a straight first wall without loop ends, but this is the first step. It would work the same way, except that, well, under hot isostatic press, the parts suffer from pressure from all directions, and well, this has some effect, as we will see. There have been some proposals, or have been proposals of how to proceed quicker with the fabrication of this thing. Here is how this direct 1 or 2 step welding works. Again, we have both halves of plates. Here is the weld line or seal which has been closed. And after dipping we hope to end up with a perfect structure. However, due to the pressure and the high temperature you need for diffusion welding, temperatures are around 1000 C or even higher. And remember what happens at high temperature and pressure. Material creeps, and this is exactly what happens during the welding process. Due to the pressure, the plate bends from both sides, and well, this is, let's say, at least a small drawback, because we want to have the plate straight, but afterwards you have to take into account that they are bended more or less, depending on pressure and temperature. Another way would be to use the same half of plates with the grooves for the cooling channels, but you could think of, well, here I have to tell you another story. Eurofair has been produced or is produced in many ways, plates, various thickness, but also in pipes. So production of seamless pipes is also a standard product, and now somebody has used these pipes, laid them inside the cooling channels, welded everything tight except of the pipes internally. They are open, and then this is pressurized, and due to the internal pressure, the circular shaped pipes will again, due to creep, start to form, and well, with time they will align to the inner form of the cooling channels. This was another idea. However, as indicated here, this always leaves more or less extended part over which is not bonded to the plate. And this again is not what you want to have in a high heat flux loaded part, because here later on the cooling channels will be overheated and will not work properly. Finally, you could go one step further. Instead of fabricating or using this usual seamless weld, you could, with much higher effort and much more money, produce rectangular shaped tubes, take them together, put two plates on top and bottom. Seems quite easy. Then you weld everything tight again under vacuum and put it in a hot isostatic press, and hopefully all these weld lines will be perfectly produced. The weld surface is much higher compared to the other studies, but well, it has been done. However, it did not work. Exactly here at these triple points, there have been very extended areas where still small cracks and voids and whatever have been left over. And well, again, on the first side, very promising ideas have been in the end not so promising. So what do you do at that point? You start with basic studies, and this we have done. We have tried to establish step by step how Eurofair behaves, what you can do, how it performs under weld. And so we first started with the examination of fabricating different surfaces for diffusion welding. We used this tiny walls of Eurofair, then by several milling tools under several milling conditions, parameters and so on, produced many kinds of different surfaces, fixed them together, welded them tight, put them in a hot isostatic press, and examined them. And for the examination, or especially quick examination, sharpening specimens and sharpening tests with the notch exactly aligned on the weld line, this is the best mechanical test you can do, because welds are rather sensitive to breaking, so sharpening tests are perfectly well suited for that. And what you can see here, the white points, that's the massive has delivered Eurofair in its initial condition, and all the other ones are with regard to different fabrication rules. So most of them are pretty near or comparable to the base material, to Eurofair, but some colors, red, yellow, and light blue, are worse, or, well, let's say, really not good compared to the base material. And of course, the question first was why? Then, what do you do if you study the influence of surface fabrication? You scan the surface and see how it's how the roughness has or could have an influence of welding. This we have done. This one was a surface which produced good choppy result. This one was the surface which produced the bad behavior. And can you see the difference? No, you cannot, because it's the same. That's a standard procedure. You measure roughness, that's its profile, but well, you can't see anything. So the next step was we really cut through the welded surfaces, examine them under a microscope, electron beam here, or scanning electron microscope, and compared which tool and which method produced what type of surface. And then we have seen that these surfaces, this red and that one, due to the chipping behavior and due to the Eurofair chipping with these tools, produced some strange break-off effects during the fabrication. And if you look on the weld lines, that's a cut through the welded plates. Here is the weld line. Then in those cases where we had bad results, there have been some voids or holes, let's say holes in the surface, which is due to this chipping behavior with the specific tools we produce the surfaces. In all other kinds where the behavior was good, you can still see, or sometimes you still see a weld line, but well, it produced good results, and so first we didn't mind that you still see a weld line after the welding. With diffusion welding, you won't not see anything after welding. That's the point. But okay, the results is what's counting, and so we proceed. The next step was to see how oxidation of the surface influences diffusion welding. So we again use the best performing surface, that's called standard surface for now, and put the Eurofair plates in a relative wet environment. Oxidation at about 70% relative humidity was done for 1 day, for 2 days, for 3 days, and for 14 days. We compared it with the base material. We increased a bit the welding temperature to 1150 C, performed the welding 2 hours with a, let's say, low pressure, 25 megapascal, and again compared it. And now the results are looking much more promising. There have only been slight shifts in DBDT, but not in toughness. And so in principle the results are looking quite good. What was new for me, or very interesting, after 1 day there is no effect at all. But after 2 days there is a shift of well, 20-30 degrees here or so. But then after 2 days, it doesn't matter how long you leave the material in the humid environment. It doesn't matter whether 2 days or 2 weeks. So this is also an interesting information regarding to industrial fabrication. You can produce the surfaces, and if you don't mind a shift of 30 degrees C in DBDT, you could store the prefabricated plates for weeks without any consequences. Then we did the same with different antioxidants or protection layers. Usually you use spray oil after fabrication to keep the surfaces clean. This has been done and also put in storage for 2 weeks. Then after that we cleaned the surfaces from the oil with isopropanol. In one case, the soap is another case. We produce the surfaces using cooling liquid during milling, or and then we welded the plates out, cleaning them after production, or again using cooling liquid and cleaning it. So again, a variation of different fabrication parameters, the same heating parameters, and again, well, there are more or less good results. In principle, the best results we have seen if you use the cooling fluid during the surface preparation milling and clean the surface with alcohol or isopropanol, then we have the best results. Then again, we have compared the weld lines with these higher hip temperatures, and what you see now is that you see nothing. There is no weld line. This is a perfectly structured Eurofair, and so in principle this was the basis for our further investigations. The next step was to examine the creep rates we have to deal with during this diffusion welding. Here is the time, here is the compression due to the creep, which is deformation, and depending on the hot isostatic pressure you use, of course, the creep rates are different, and about 2 hours, this is the typical welding time. So if you would load or compress the plates with 20 MPa for 2 hours, we would have to account or take into account 5% creep deformation, which seems to be a lot and really affects the whole design and fabrication process. So here, the most important principle, you have to try, or we tried, to reduce the stress as low as possible and still try to get a good weld line. In principle, there is for diffusion welding, you need very high temperature and very high pressure. Then bonds will fuse completely together. But, well, of course, if you have to take the creep into account, then you cannot use these very high pressures. So we transferred all these basic examinations into a mock-up fabrication. This was a small piece with a 7, if I count correctly, cooling channels as a closed box. And if you load such a plate with a hip pressure of 7 MPa, you see the real stress throughout the whole plate varies from 10 MPa at the border, and internally at this distance parts between the cooling channels raised up to 26 MPa. And remember, 26 MPa will produce a creep deformation of more than 5% already. So anyway, we gave this to industry to press it together or to weld it together, and then reality came into play. The workshop forgot to dry mill the surfaces and immediately vacuum sealing, so the parts have been stored for us, for at least a week. I'm not sure how long it really was, but it was certainly a week. After then, they only welded them tight, and okay, the pressure was the hot isostatic press was not able to deliver only 7 MPa. It starts at 10 MPa, and well, without asking us, they said, we don't mind 7 or 10 MPa, this doesn't matter, and so they fabricated this 10 MPa. That's reality. So again, was later on when we knew this about this. And so the real stress distribution over the blade looks like that. In the end, in the middle of the blade, we had a maximum of almost 40 MPa pressure. And okay, this resulted in what we expected. The blades, especially in the middle, have been deformed immensely. Here is the profile. This should be a straight line, but well, in both cross directions you have a severe deformation of the whole blade. And so what at the beginning looked rather promising, in the end resulted in such severely deformed blades which cannot be used for a first wall. Also another funny side effect was that since the blades are not perfectly straight and you have seen there is some roughness in it, due to the pressure on these blades and due to creep and diffusion, there is a material flow outside of the end of the channel, which produces, well, not so big, there are a few tenths of a millimeter, but still internally in the cooling channel you have long, strange features along the weld line. That's a side effect which we didn't know before. So we had good parameters to produce this. Everything is okay. High temperature, high pressure leads to perfect welds, but unfortunately it leads to a completely useless component. So we have to think about better ideas again. Better stability would require low temperatures and low pressure. Then we had a good component theoretically, but then the blades didn't glue together, they would come apart, so also a useless component in the end. We have again thought about it and with we I mean the whole fusion community, and the question was how could you really use high pressure and also high temperature and avoiding this bending due to creep. One method again would be to use these rectangular tubes between the blades, or this tube forming was also the right idea going in this direction. And well, the other idea is something in between. That, as said, for a first step, you use a really low pressure, as low as possible. It must be so low that the blades are not bended, but the channels will still at least partly be closed. And then you open the channels and will put full power into the hot isostatic press, because then due to the internal and external pressure, this would avoid creep and hopefully close the cooling channels in between. This was at that time state of the art, and afterwards you still had to bend the whole thing with the internal cooling channel and pray or hope that this bending does not somehow destroy the internal cooling channel around the bended blades. The pros and cons are well known now, and well, we thought was not very promising or feasible, and so we had to think about additional things. This is what I have just mentioned, such a form stable fabrication processes. There was one idea from CE8 that you use blade, mill these grooves of cooling channels in it, and then you weld 3 meter long thin plates on top to close the cooling channels. Then you would end up in such a configuration, and now the cooling channels are tight here. You could do this with laser welding, for example, or whatever. And in the next step, you could easily diffusion weld a thin plate on top of that, so you don't have to worry about bending of the whole cooling channel arrangement, because now the channels are open, and this is just diffusion welding two plates together. This is certainly a feasible idea, but now if you think on the fabrication of hundreds of first walls, and each of these first wall has, I don't remember, 40 or 50 of these cooling channels, each 3 meter long. So 3 meter times 50 times a few hundred, you come to end up with several kilometers of this very tiny and delicate laser lines, laser beam weld lines or whatever. And if you have only one tiny leak somewhere in between, you will never find it, and it will certainly destroy the component. So theoretically it's feasible, but risky. Another thing or another method from our side was, okay, to prevent the channels from bending, we fill them up, we put simply a massive steel part or whatever in this cooling channels, and then you can press the plates together with pressure as high as you want, and it prevents them from deformation, and afterwards you remove the solid parts and you end up with what you want to have. In principle, easy idea, we have done this, fabricated plates, 2/2 of them, then we used simply stainless steel, and well, the trick is to remove the parts after welding. So we have coated them with a separating agent, with vitriol, put them inside, again welded all these surface lines together in an electron beam welding chamber, and after that, yeah, you see here, this is easy to do with an electron beam facility, and then we hipped it, and you see the inlets could easily be removed, and in the end it was a perfect plate. So in principle this could work. We haven't tested it on a real 3 meter long component, but well, it was a first success to fabricate accurate parts. But we thought, again, I didn't show you all the drawbacks, which in reality there are. You still have to take into account, but I say in principle it works, and so we thought about another method, because if you do already all the work to fabricate these inlets, well, how to use inlets made of Eurofare with a thickness of 1 millimeter and leave them inside. Or in other words, we thought about how to fabricate such pipes in the right dimension out of Eurofare, use them as inlets and leave them inside. These are several steps. You put them together, then again at the end and front you have to weld the whole thing leak tight in vacuum, press them together, and this is what we have done. And well, I think this is a rather promising idea, which has many advances. These are the steps. You have first to bend the big massive Eurofare plates for the U-bends. Then in each of those halves you have to mill the grooves for the cooling channels. Then fabrication and bending of pipes is an industrial process. I will show you an example later. That's also easy. Assemble everything together. You can use all standard equipment. Tight sealing on the vacuum with electron beam is also standard, and at the end you produce high pressure and high heat temperatures. So in principle this is all you need. And now you have to remember to a few things I mentioned yesterday. If you want to bend massive thick Eurofare plates, that's not so easy depending on the bending radius. What we have done here is we have we have performed a heat treatment step on the Eurofare, and that way that Eurofare does not transfer into the martenite, this hard and strong material, but we use a very low cooling rate, and in that way it produces perlite. And perlite, if you remember, is very, very soft and therefore easy to bend. And this is one of the advantages of chromium steels. Okay, summary, we bended the plates. That you can do this on real size dimensions also. You see here in this picture, this is how they produce at the moment or during the last years the real test blanket modules. You have to soften the Eurofur by perlitization, and then you can bend them, and that's it. So first step, no problem. Second step, to mill grooves into these bended plates, it's also no problem. We have seen this. Then the fabrication of these inserted pipes. If you start from thin stripes of steel, then there is a big industry behind who performs or produces any shape, any profile of pipes. They bend the sheets around such a, well, according to your profile you want them to have, and then they weld the sheets together. Again, you can choose whether you want to have laser welding or tungsten net gas welding. In the end, this is relatively cheap and easy to produce, and you can buy such pipes in any shapes, in any material. So this we did. We produced these pipes, also bended the pipes, put them or inserted them in the prepared halves of the first one. This is how it looks afterwards. Then again, you have to weld it together, hit it, and that's it. At least in theory. Then we cut here the ends apart and had a look on it, and now what do you expect? A perfectly shaped and welded part, aren't you? And in this case you are right. This is a micro image of the weld line. I don't know whether you can still see any left over of the weld line. Well, at least not from your distance. If you are very, very careful, and well, you could at least imagine that there, at some parts, there still was the end of the one or other plate. But in principle, it looks perfect. We examined them by non-destructive methods and also by tests. Indeed, this was one example for a successful investigation, and well, which criteria were fulfilled by that. We can quickly scroll through them because all the criteria fulfilled. That's it. So this was one example for a specific fabrication in fusion applications. Now we have the U-bended first wall from such a blanket box. But that's not the whole story, of course. We have to continue. This first wall we can produce now, no problem. But what about the caps? That's the green parts to close the box. And again, the cap looks similar like the first wall, except that here we have a meandering cooling channels. The trick here, or the problem here, is not to fabricate the caps. This could be done similar to the first one, but you have to perform a weld along this line. So more or less a weld line is 3 meters long, which is not a problem. Also the bend is not a problem, but the thickness of this plate, of this cap, is about 40 millimeters. So you have to perform a 40 millimeter deep weld. And at the vicinity of the weld, there are already the cooling channels. So the weld has to be quite narrow, deep, and long. And this is the difficulty with such a weld. First thought again was, well, let's use electron beam welding. This we already knew worked pretty good in all these simple sealing cases. And what we have done, gone to industry, they have really big machines and electron beam facilities where you can perform 40 millimeter deep welds in steel. You see it here. this is the top, the beam comes from that direction, and in the end it produces here a weld between those two plates. This was the arrangement, two plates together. At the bottom we have put a beam stopper for some reasons, and in the end it looks fine. It is narrow, it is deep, looks quite homogeneous without any defects, and so we thought, well, it was easy peasy, no problem. But there's almost always a but. If you examine the weld more detailed, then you see that there have been some phases which don't belong into Eurofare. And now you have also to remember yesterday formation of delta ferrite. Delta ferrite is a phase at the very high temperature near the melting point, and especially during welding with rapid cooling there is a leftover of such ferrite formations which do not transform into martensitic structures. So these red dots here are all delta ferrite. Delta ferrite compared to martensite is very, very soft, and this means you have many very, very soft spots into the weld line, and this causes problems later on. Then again we said, okay, no problem. We have the machine, the knowledge, whatever, we can push many buttons and change parameters, and we really did it. I don't want to go through all these things. Here is just another example with a variation of many things. And okay, we have been able to avoid delta ferrite variation, but then we ended up with big bubbles in the weld line. So, a long story and a short conclusion. We have been able to produce a perfect weld, not a perfect weld, a good looking weld with delta ferrite on the one hand, or a delta ferrite free weld but with big bubbles inside. In the end, all useless. So again, with hardness profiles, you could see all these blue colored spots are rather soft due to stellar ferrite formation. The properties before and after welding you can see here. With and without heat treatment, that's another point. We'll come to that later on. In the end, well, this is very optimistic. Optimization required. In other words, or in my word, well, failure. Complete failure. Forget it, don't use it. So, other ideas had to be looked for. Next option was to do it by tungsten inert gas welding, TIG welding. TIG welding makes use of arc, of an electric arc. This produces high temperatures. Then you have to use also welding material, weld wire or filament wire. This will melt under the arc, and so you fill up the gaps between two parts and join them together. This is in principle the trick by inert gas welding, but here you remember we have a very narrow and deep weld, and this makes it rather complicated, and this is not standard. At CEA in France they developed the possibility to do this narrow gap welding with tungsten inert gas. This is the electrode. This is a gap, in that case, between a tube of austenitic steel, which is used in fission technology, and here it works. Here you see a movie of such a weld process. You can see here the electrode, the arc, and somewhere here at the bottom is the filler wire. Again, I spare you all the details. In principle it works, but for 40 millimeter deep welds and Eurofare, the drawback is that there are so high deformation levels due to the temperature differences that it didn't work perfectly. So let's come to the next option, also a very specific, probably unique weld technology at CEA, they developed a mix of laser welding and using a laser filler wire. In principle, it's TIG welding without TIG. Well, it sounds strange. You use the weld material, the weld wire, but melded by laser. That's the principle. Again, this comes from fission technology. Also here it worked quite good with austenitic steels. And this was transferred to Eurofair, and you see such a hybrid laser welding, or whatever they name it, seems to work quite good. Here are the several weld layers which have to be brought up in various steps, and depth here of this weld is almost 20 millimeters or so. So in principle it could be applied also to these 40 millimeter deep welds. They arranged all the setup of the machinery, and here you see the working narrow gap. Oh, that's the wrong topic here. It's a narrow gap hybrid welding, and you see the heat or plasma, whatever is here produced, distribution is a bit smoother compared to the real TIG welding, and so in the end this looks very promising and is at the moment our favorite for the production of the first wall to join with the cap. Now we have the U-bend with a lid and on top and bottom the caps. Now let's come to the internal structure of this blankets. There has to be produced a grid. This grid is also internally with even more tiny cooling channels. So these are delicate plates, and they have also to be welded together in order to form grids, which means you have to perform the weld line all on these cross sections here. And again, internally there are many delicate channels. Here you can see it better. This is where the plates are crossing. There is one vertical plate, and here the horizontal plates, and they have to be welded there and there with the vicinity of small cooling channels which don't have to be destroyed by the welding. Again, there are tiny distances, relatively thick plates, I guess in the range of 10 millimeters. And okay, the problem here is not welding. This can be done by preferably laser, but also TIG welding. The problem here is that you have to perform these weld lines in a box, which is almost a meter deep, and it's, well, by hand it's not possible. You cannot crawl through these boxes or whatever. So the problem is to have a tiny aperture to go where you can go back and forth and weld this. Up to 7 years ago or so, 4 kilowatt laser welding was done for that part. Then they updated their equipment, and also here we don't have to go into detail. And the principle of laser welding is that you, like in electron beam welding, you don't normally use a filling wire, you just press those parts together and melt them along the weld line. Now with beam welding, the problem is that there is a pressure along the beam, and this, I have pictures later on, presses usually the melt down through the weld line. That's why they've used here a substructure beneath the weld which reflects the heat and keeps the melt within both parts. This you see here. Here are both plates. They have to be welded along these lines, and this is how it is done. Here is the laser beam and weld. moved along the line, and in the end, it was possible. This here is the weld structure, Y shape. Was possible within a single pass in these tiny dimensions. These are 10 millimeters, 10 millimeters thick, to produce this weld without destroying these delicate cooling channels internally. Sometimes you also have to, well, if something is happening during the process, you have to recurve welds, which requires then a second or even a third welding pass. They have done this here intentionally and welded the same structure a second time. And even if you do this a second time, there is only a slight distortion of the cooling channels and still the weld looks good. So this is a perfect measure of producing the grids. We have the box with caps and an internal grid. This can be done by all technology I've shown you, but the real box or the real blanket looks about like that. So it's very difficult with all these internal pieces. What you see here is that is breeding boxes to produce, which will produce tritium, the fuel for fusion, during operation. They have to be fixed in the grid of the box. They will be shifted from the backside, like here, into the box. And these breeding units have also to be welded together. So if you look or have a look on this structure, you can imagine that there are many, many welds of very different shaped boxes and varying thicknesses. And well, you cannot develop for each and any case a specific welding technology. So for these thinner plates, there are then only a few millimeters thick. You have to use standard weld fabrication tools. Standard welding still means thick tungsten net gas or standard laser welding machines. So we focused on that, compared it since electron beam welding could also be considered more or less as a standard fabrication good, and focused on the effect of welding in general in Eurofair for the fabrication of such breeder units and their specific requirements. The requirements are wall thicknesses between 4 and 10 millimeters, and especially for these breeder boxes there is a restriction. I haven't mentioned yet, but well, you know it since it's obvious. If you melt Eurofair and cool it down, then it produces martensite and is hard and brittle. So after welding it's the same as after quenching. You have to perform a heat treatment. Then you could think of two types of heat treatments. One was pushing the reset button, as I said yesterday, repeating a fully heat treatment, acidization or solution annealing, quenching and tempering. And with that you should have completely restored material and all the weld effects should be away. And indeed with Eurofair, it's in almost all cases this is perfect measure and works. But here in this case, in the case of these breeding units, you have to remember that they are filled with beryllium pebbles as well as with lithium ceramics. And if they are filled with that pebbles and you have to close or these boxes by a final weld line, then you cannot perform the full heat treatment anymore, because this beryllium and especially the beryllium pebbles cannot be heated higher than, well, let's say 700 or maybe 750, but it's a delicate thing. You want them to be as cold as possible and probably not heated much more than 700 C. This is the restriction. So for especially these final welds, which will close the breeding boxes, you are restricted to a only tempering treatment after weld. And this means also you cannot perform this austenitization treatment, and therefore we made some general investigations. What is the lowest possible effective austenitization treatment and what is the lowest possible tempering treatment for such welds. All other things are valid for the other production goods too. Some parts are hardly accessible. This is another problem. Extreme different geometries. I have already showed you what you can do here. And well, the high density of the weld seams is related to material problems and reproducible data and warfare weld. That's also a general problem which is related to the codes and standard. Here, in principle, we need much more data, as I have also mentioned during the last day. But let's focus now on the fabrication of this breeding units. A typical weld geometry for tungsten inert gas welding is that you have a gap between both parts which are to join, and a simple case is a half V notch. This is in that case a 45-degree notch on the one side of the blade, and since there are internal cooling channels, you have to avoid that the weld is going outside the back end. There is also a small step at the final stage. The problem with beam welding is that if the beam is too strong or has too much power or is too long on the same spot, then the beam goes completely through both parts. And so it produces, especially if you weld pipes or cooling structures, you would produce material which goes into the cooling channel. That's why we tried to stop a beam by such a rectangular arrangement on top. For the TIG weld, again, the gap is filled with welding material, with a wire which is welded, whereas in the beam welding cases, you don't need additional material. Here, the blades are liquefied. First step always is preparation. You can do this on the large scale in the industry. It's done by pickling, by using acid to remove oxides or whatever. We tried this with Eurofair, used such standard acids or pickling treatments, and the result was, as is often the case with Eurofair, not as expected. It was produced not a good surface. It doesn't work. I don't know why, but with this 9 chromium steel, at least our trial has resulted, has not resulted, was completely unsuccessful. That's why we avoided them and said, okay, perfect surface. For a perfect surface, you have to dry mill without any liquid, a little bit of the surface, then it's shiny and perfect, and then you have to hurry up and start with welding. This was preparation in all cases. Here is what happens if the intensity of a beam, in that case electron beam, is too high. Here it is too low, then the weld doesn't go through the whole plate thickness, still too low. Here it is perfect, where the weld goes completely through from top to bottom. Then, if the beam current is too high, you push material out of the plate. You see it here. From top it's removed and you push it completely through and out of the weld. So, these studies have always to be performed on the real material to adjust the weld machine. So in that case, 21 milliampere have been perfect. What is not so perfect is that, well, if the plates vary in thickness, you always had to adjust exactly the beam if you don't do this, then the beam stopper isn't liquefied, it's left over and a perfect crack initiator for the structure. So these are the most problematic zones for the beam welds. Other drawbacks of beam welding is that they easily produce bubbles inside the material, depending on the gas which is still in any steel or material. Also small voids, like here in the laser beam weld. Other drawbacks is if the volume of liquefied material is too large and the quenching or solidification rate is too high, then you are typically left over with cracks or holes along the solidification line inside the weld. So cooling down after welding, or the cooling down rates after the welding or during welding, are also very important for beam welding. It's completely different for this tungsten inert gas welding, because here you control layer by layer the joining. The drawback here is that the dimensions of the weld, they are really huge. They can be several centimeters in the end, depending on the dimension you are doing this. And again, also you use additional Eurofer material in form of typically 2 mm thick wire, and this also could produce or can produce problems, since this weld is permanently melted at very high temperatures. The one or other alloying condition element could evaporate, which would change the chemical composition of the resulting weld. Good. Now let's have a look on the microstructure we have produced, as several parts. The laser weld has produced the narrowest weld line. It's only 1 or 2 mm thick. Then electron beam weld, even here in that case it was not properly adjusted, produces a V-like shaped resulting weld, and depending on the thickness of the plates, this half V-shaped tungsten inert gas weld produces very big volumes looking like that. And now, again, due to the transformation behavior of microchromium steel into martensite, depending on annealing and quenching and tempering, and due to the temperature distribution over the weld surface or volume, you produce constantly in the whole weld line here base material at that point, completely hard, not untempered martensite here, where all the material has been fused and cooled down rapidly, and in between it's a mix of lowering annealing temperature and well, at that end higher tempering temperature. So what you produce is a Eurofer type, which is quite soft here and very fine grained, and extremely hard and untempered in the middle. So in the end it's a variety of many different and contradicting properties inside one weld. The same is here with the beam weld, of course, but the so-called heat affected zone, where the transformation was not unique or perfect, is smaller compared to the tungsten inert gas welds. You see it also here in the hardness profile. At the end here, this is the base material property from Eurofer in terms of hardness. In the middle of the beam or thick welds, we have very high, very hard material, and at the end, there is, you see, especially in the thick welds, there is even a much softer material, or much softer variant of Eurofair. And that's all due to the temperature distribution over the weld surface or the cross-section. Again, these are things you usually should avoid, these leftovers of the beam stoppers, and this is quite difficult to perform with laser because, or this kind of laser welding, because it produces a very narrow weld line. You always have to target perfectly on this weld line. But let's leave this beside. These are the welds we have produced. You see here, etched, this is the weld microstructure with the heat affected zone and corner. We performed Sharpie specimen tests with notches directly in these welds, but also with notches centered at these heat affected zones. And tests without any further treatment, no post-welding heat treatment as it's called, looks like that. This is the Eurofair regime for Sharpie tests. The red one, that's electron beam welded, which looks not good, but it's still the best of all these variants. Laser weld is here, and this tungsten net gas welded are there. So without any heat treatment, I wouldn't use these welds in Eurofair, but this we already knew, but here you see the effect in terms of Sharpie testing. Again, this was with the notch directly in the center of the weld, and now the same result or the same test with the notch at the heat affected zone. Then all of a sudden the tungsten nut gas welded Eurofair specimens don't look so bad, but still tungsten nut gas with 5mm thin plates that don't look good. I don't know whether this is question of where exactly the notch is located. Could depend that if you are, the dependence on that could be in the vicinity of a few parts of a millimeter. Could also be, I don't know, a very specific thing of these SIG plates and filler material. But in general, you see, without any post-weld heat treatment, we have a severe degradation of material properties in terms of embrittlement. So these welds in Eurofair are in general brittle if you don't heat treat them. Then the same exercise again, but with a heat treatment. Here we started to examine if you could live with only one heat treatment as low as possible, keeping in mind the breeder unit specification. So a heat treatment of only 700 C for 2 hours results in such a picture. And this is quite promising. The EB welded parts are perfectly in line with the base material. Also, the laser weld is at least near the results of the base materials. And don't be astonished that we hear that some of the welds show even higher energies in the fracture compared to the base material. That's only a geometrical thing. The fracture in the Sharpie properties, they propagate along the weld line, and in the base material they propagate straight through the material, and such bending in crack propagation requires higher energies, but this doesn't mean that this material is tougher than base material. DBDT, that's the right measure, and you see that's perfect here. So you could, in principle, live with electron beam welds, laser beam welds, with only a 700 C post-welding heat treatment, and then the beryllium pebbles won't suffer so much. So this could be a solution. Again, the same test with notches in the heat affected zone. Electron beam and laser beam are not as good as the base material, but well, you could still live with it. But here also tungsten nut gas welding, at least with the thick plates, doesn't show so bad. Nevertheless, the weld sander doesn't perform good, so forget about welding here. Now finally a few images, view graphs of typical defects you still have to live with. Specifically here with tungsten and nut gas welding, there are also precipitates, bubbles, whatever left over in the weld. And you can see that even the B welded parts have obviously some bubbles in the material, but again, even if there are such tiny bubbles or voids, whatever, tested at minus ATC, this never was the cause for brittle crack propagation. So you have to live with it, and you can live with it if there are not too much. The same enlarged here, beautifully shaped crater-like crack pictures, but things you don't really want to have. Also here in laser seems to be also some precipitates shaping during the melting. And well, in general, if you melt material, quench it down, that's not the best process for any material, also for Eurofair. Here is a very broad overview on many different kinds of heat treatments. We try to optimize that to go even below 700 C with 680 C to increase the time to 16 hours. Then we studied the improvement of even higher temperatures and a full heat treatment with as low as possible solution annealing, and all this affects the hardness, that's clear, and the red marked treatments have been examined closer, and again, always the charting results. On the first view, red and blue looks good. Now let's have a look what red is. Red means thick welded and a complete heat treatment with 900 C solution annealing and 740 C tempering. Well, you can use this for the production of these breathing boxes, but it's not astonishing that here we have a full recovery of the weld. Blue, that's also very promising. Blue is also tungsten nut gas welding with only 740 tempering. That's still too high for the breathing boxes. Then next would be yellow. That's an electron beam again with 700 C. This comes not quite, but near to the baseline base material. And you certainly can't forget this orange and green. Orange is only 680 tempering, and you see this difference of only 20 degrees in tempering has a very big effect in the shift of DBDT. So this is brittle, this is not so brittle. And finally, green, TIG weld. It never works if you temper it with only 700 C. So as a conclusion, for TIG weld, you need at least 740, which is too high for the breathing boxes, or electron beam welds, which need at least, or well, which could be useful at 700 C tempering treatment after welding. A much more complicated problem is then connected to creep, because all these boxes are stressed under high temperature, so creep has always to be taken into account. And also here, just the broad view or the broad picture. We made many creep tests at various temperatures. Operating temperature finally would be not higher than 550 C. see, but to speed up creep test, you don't always have years of time to wait until the end of the creep test. That's why you perform them also at higher temperatures. And you see in all cases the colored curves are below the gray ones, and gray ones, this is base material, and the colored ones are the joint materials. So whatever you do after welding, the creep properties are worse compared to the baseline materials. In the best possible case of a post-weld heat treatment, you can see here these are the green dots, and green again means a full heat treatment, which is always useful for Eurofair welds, but again cannot be used for these breather boxes. The best one in terms of Sharpie test for breather boxes was the yellow, this 700C tempering, and you see here with regard to creeping, this is the worst possible case. And most often you have some contradicting material properties, and creep compared to the Sharpie property is indeed contradicting. This is how the specimen looked after breaking in the creep test, and the only interesting and important thing here is, and you can see it best in this specimen, this here is the electron beam or laser beam weld, this small area. And this keeps completely its diameter, and the necking appeared a bit on the left side and on the right side. And this is a general observation for all these creep tests and all these welded specimens. The fracture never occurred in the heat, never occurred in the weld. It always started where the material is very fine-grained, and if you remember, a fine-grained material delivers the worst creep properties, and that's why all this necking and finally breaking of the specimen occurred outside of the weld, but not completely outside, right at the vicinity of the weld, that's in the heat affecting zone. This is the weak point of Eurofair welds under creep load. Tensile test, that's the same, and this is an overview of several hundred welds, very concise and very simple to interpret. To test these Eurofair welds without heat treatment by tensile test is completely useless. You could already have predicted the results, because what happens? Without heat treatment, you perform in any case hard martensite, and this is a very strong material, and it will never break in the weld, cannot, because the base material is much softer, so it always fractures or breaks in the soft area, in the base material area, and so in the end what you are testing is the base material, and that's why here all dots show the same line, regardless whether this is unwelded Eurofair or welded Eurofair. So if ever somebody wants you to test a welded Eurofair by tensile test, tell him, forget it, it's useless, you don't. I forget to ask you before, but nevertheless. This is an overview of all these tensile specimens, and well, you cannot see it quite clearly, but believe me, all these tensile specimens have been broken outside the weld, in the base material. Well, that was a more or less comprising overview on Eurofair welds. I have 20 single conclusions, which I leave to you to read them for yourself if you have time in a copy of the lecture. Thank you. coffee or a question?
Thank you.
Maybe you should use the microphone.
In the first step, when you talk about the fabrication of the cooling system, the cooling tubes, you talk about and focus on the surface microstructure and the variation of shape or grip, but you didn't say anything about the change of the microstructure of the build, and you are using 1000 degrees. I think this is important.
Okay. This is, do you remember yesterday? There I have shown you the hardness curves of Eurofare up to 1150 C. So at 1150 C, you produce, well, we are in the regime of austenite, with very big, huge austenitic grains. And so during hipping at 1150 C for 2 hours, this is exactly what happens. Eurofare transfers into austenite and produces huge grains of it. Huge meaning, I don't remember, 100 to 200 micrometers, something like that. And during that phase, and due to the high temperature, and also due to the fact that diffusion in austenitic steel is quite high, you perform a quite good or a pretty good diffusion weld. Both plates bake together, more or less. And then you switch off, or the hip is switched off, pressure released, temperature goes down, and then you remember the TEM movie I have shown you, what happens with the austenitic grains, they transform into martensitic glass structure. So in the end, after hip, what we have is a very hard, brittle Eurofare condition, martensitic structure. And now your question probably is, what is the next step? Because in that case, you cannot use, of course, this part of first quad. The next step would be to put the whole thing into a big furnace and temper it again. It is martensite now, but well, it needs a tempering treatment, a final of, let's say, 750 C for a few hours. And then it is quite soft, and the microstructure is, yeah, as in any Eurofare steel after that heat treatment.
One question. So you have to continuing the question that the colleague had done. If you are going to weld the caps on the top and bottom of the tank, 40 millimeters thick, you have to post-weld heat treatment again.
Yeah.
So you have to go inside the furnace again. And what are you thinking about to avoid any deformation of the whole structure?
Yes, this is completely right, and I avoided this to mention during the session, but it's, both your questions are perfectly right. And yeah, the final conclusion here also was welding without post-weld heat treatment is, well, it's not possible. But in that case, well, in your case, okay, it's not so difficult to heat it up to 700 C or so. Okay, you have to avoid some distortion due to tempering, but that's a smaller problem. The problem here is this 40 millimeter thick plates and depth of is more tricky. It also requires a heat treatment, that's clear. One thing you can never do in both cases is to perform the full heat treatment, which would always be preferable in any Eurofare application. But for example, by induction heating, you could go along this 3 meter weld line, and so depending on the induction effectiveness in terms of penetration depth and heating up, I'm sure you can do a local post-weld heat treatment along these weld lines. There is no other possibility. And otherwise, in any case, you have to live with a non-optimum treated material, but this is true for each and any case. Good, coffee break.